All right, so here to wrap up this section, a couple of more properties of determinants. All right, the first one is we're going to look at theorem SMZD. All right, and this one has to do with singular matrices. Right, so a square matrix is singular if the determinant of A is equal to 0. All right. Now here, just we won't go through the proof itself, but here just kind of why that has to be the case here. All right. So if we think of a matrix being non-singular, right? So the determinant is non-zero if the matrix is non-singular. Excuse me. If the determinant is non-zero, then the matrix is non-singular. All right, and the square matrix is singular if the determinant A is 0. All right, now think of why that must be the case, right? If A is non-singular, I know it reduces to IN, right? Okay, but if it does not reduce to IN, then it's singular, but that would mean that it would have a row of zeros, right? And once we introduce a row of zeros, then the determinant of A is going to be 0. Okay, so that's really the idea behind this proof here, right? If A is non-singular, a row reduces to IN, right? And the determinant of IN is 1, which is not 0, right? Tracking the row operations back gives the determinant of A to be 0. All right, so all this means here is now we have another way to determine whether a matrix is non-singular, is the value of the determinant, right? So really, and what we'll find out is what I care about in calculating the determinant is if it's 0. If it's 0, I know it's singular. If it's non-zero, then that just tells me that it's non-singular, right? What the actual value is, really, it's not important, right? I think usually I get questions like, well, what if it's positive, negative, or if it's really big? Again, it doesn't really matter, right? The only thing that matters is that if it's 0, it's singular. If it's non-zero, it is a non-singular matrix. All right. So now we can add here. We can go another round at our NME theorem. All right. So that gives us here rho NME. So now we're at round 7. So let's take a look here. All right, so theorem NME, adding this latest condition here. So we left off round 6, talking about the rank and the nullity. And add to that, the determinant of A is non-zero, then the determinant of A doesn't equal 0. So that's all equivalent, right? If this is true, non-singular, null space is the trivial null space, the nullity is 0, the rank of A is n, etc., right? So now we add another condition here. All right. So we have that. All right, now a couple of other properties here. So we wrap up this section. We have okay. All right, so the determinant of AB, right, as long as both A and B are square matrices, right? A and B same size. Then that is equal to the determinant of A times the determinant of B, which is nice. It respects multiplication. All right. All right. which is an interesting kind of development here, since we've seen that matrix multiplication is not commutative, right? But here the determinant just converts into ordinary scalar multiplication, which is commutative, right? This would be equivalent to the determinant of B times the determinant of A, right? But again, B times A is not necessarily the same matrix, right? Some interesting kind of properties from here. All right, now a couple of applications here for the determinants. All right. We have that the determinant of the inverse of a matrix is equal to 1 over the determinant of A. All right, and the determinant for A to the K power is, since it respects multiplication, right, here, right, this derives from that, is the same as the determinant of A, and then just raise it to the Kth power. All right, oops. All right, and lastly, if AB is equal to the identity matrix, right, then the determinant of A times the determinant of B must equal to 1. Right? But more importantly here, neither can be 0, right? So A and B are both non-singular matrices. Okay. All right. So here we have properties of the determinant. And again, what we really are after here is, for the most part, is just to use the determinant as a way to determine if a matrix is non-singular or not.